Let's keep going with the chapter 20 practice problems. Let's do number 6. So we have 24 volts here. And at what rate is thermal energy generated in the 20 ohm resistor? So what we're looking for power. Thermal energy has heat. At what rate is heat dissipated through this resistor? So to get power, we need 3 of the variables I, V, and R. We need 2 out of those 3. We only have R. We don't know V yet. We don't know I. So what that means is we have to work backward again. Simplify the circuit and then work backwards. So once again, I'll draw the original circuit. And I'll call this R1, R2, and R3 over here. So the first thing is that R1 and R2 are in parallel, so I'm going to simplify those. So it's going to be R12. And in parallel, use the 1 over equation, 1 over R1 plus 1 over R2. And when you do this, when you solve for R12, you're going to get 10. When you do 1 over 15 plus 1 over 30, and take the reciprocal, you're going to get 10 ohms. And then you have these two in series. So that's my R equivalent. So R equivalent is going to be R12 plus R3. So just add the 10 and a 20, and you're going to get 30 ohms. And now we want to know the 3 variables here for this R equivalent. We have the V is 24, so we can find the I is V over R. 24 divided by 30 is going to give us 0.8 amps. Then we're going to work backwards. We're trying to get back to the 20 ohm resistor, which is R3 this time. So R3 and R12 were in series to get here. So that means that in series the current is the same, so we know the current through number 3 is also 0.8 amps. And the resistance is 20. And we're trying to, well, that's all really. We don't have to find the voltage here because now we have the current through R3 and we have the resistance, and that means we have 2 out of these 3 variables. So with that, we can find the power dissipated, the energy dissipated through this resistor is going to be I squared R. That's one of the 3 equations. So do 0.8 squared times 20, and you'll get 12.8 watts, which is closest to 13 watts. So really pay attention to which resistor is asking about. Once I had written I3, I was ready to start calculating the voltage, but I have to stop myself and see, wait a second, I have everything I need. I don't need to calculate voltage. I don't need to go back to this step. I have everything I need for R3 here. And R3 over here has not changed. So I can stop right here. This is everything about R3. Now, if it had asked for the thermal energy generated in the 30 ohm resistor, right, then you would have had to look at R12, calculate V. Once you calculate V, then you go back one step and say that the voltage here is the same, and now you'd have to use R1 and V1 to find the power through this one. But we didn't have to go back that far. Let's keep going. Let's do number 7 and 8. So we have an RC circuit. We have the battery. Now this is just an ammeter that just measures the current. So we don't even really need this because the question could just say what's the current in the circuit instead of what's the current reading. So they're all in series, and our RC circuits that we deal with, they're always all in series like this. And the switch is open, but then we're going to close the switch. So when we close the switch, that means we're going to start charging the capacitor because there's a battery here, so current is going to flow and charge this. So what's going to be the current? Well, if you remember the charging capacitor, the current graph looks like this. The current always starts high and drops. Because what happens is, as this thing becomes charged, then it's harder for charges to flow because a potential difference begins to accumulate here, and then less charge flows. But at the beginning, when it's not charged, Q is 0, and delta V is 0 at the beginning. Then that means you have the maximum current flowing through here. So to find that maximum current, we can just use I is V0 over R, where V0, you could actually write it as E is a 6 volts. So 6 divided by 4 will give us 1.5 amps. And just to make sure that you understand this graph, so what I was saying about how you have to have the maximum current first, is because once this thing gets charged, well, let's say that this has the full 6 volts on it because it's fully charged. That means this is at 6 volts, this is at 0 volts. Once it's fully charged, then you have no more potential difference between these 2 points here, and that's when current doesn't flow, when it's fully charged. So that's how you know that when it hasn't begun, when it is just starting to charge, that's when you have the maximum current. Number 8, what will be the charge on the capacitor 10 minutes after the switch is closed? So we're looking for charge, and it's a charging capacitor. So we're looking for this equation here that says it comes from the charging capacitor, 1 minus e to the negative t over tau. So we need to know the initial charge first. So the initial charge, this stands for maximum charge. Right, because in this case, because you remember this graph, it looked like this. Your capacitor was charging. This was Q. And when you have a charging capacitor, this charge is initially 0. So this Q0 is definitely not the initial charge because you start with 0. So if you had 0 here, then you'd always have 0. So this Q0 actually stands for the maximum charge here. And you get the maximum charge when you have the maximum potential difference across here. When you have the full delta V is equal to 6 volts, when you have that full potential on here. So then you can use C equals Q over V to solve for Q, C times V. So you're going to get 0.6 microfarads, that was the capacitance, times 6 volts. So you're going to get 3.6 microcoulombs. That's Q0, which is the maximum charge. And then the only other thing we need is we need tau and we need time. So time is going to be 10 minutes, but it needs to be in seconds. So that's 600 seconds. And then we're going to have tau is defined, the time constant is defined as RC. R is 4, C is 0.6 microfarads, so you're going to get 2.4 microseconds. So now you're going to plug and chug 3.6 microcoulombs here if you just leave out the microcoulombs, then you know that your final answer will be in microcoulombs, so you don't have to put them in the calculator. Over here, though, you've got to put 1 minus e to the negative 600 divided by 2.4 times 10 to the negative 6. Since the units don't cancel out, you've got to do that. And what you'll get is you'll get 3.6 microcoulombs. Now, this goes back to what I mentioned in class, that you always want to see if there's a shortcut. So the point is that once you realize that tau is 2.4 microseconds and that it's asking for something after 10 minutes, 600 seconds is much, much, much greater than this time constant, then that means that you've already reached here. Because this is about, what, 3 or 4 tau? We said by 10 tau, you basically have your maximum charge. So by, what, 250 times tau, whatever this number is, you know you've reached your maximum charge. And this was your maximum charge right here. So you didn't actually have to spend time putting all these numbers in here if you looked at that.